this is Rahul here. My roll number is M23 CSA 522. I'm here to present my presentation on the paper. So my paper is titled as basically it is based on the long chain of thought. So the paper is titled as something like this is my paper title. Let me think a long chain of thought can be worth of exponentially. So it was presented in the recent 2025 Neura IPS. So this is a very good paper, which basically clearly indicates that the long chain of thoughts are exponentially better at reasoning a given task. As far as reasoning task is concerned, uh, the sequential long chain of thoughts are much better and advantageous over the the breadth of task or the parallel task that you can give. So let's get back to the paper. So basically, the paper, this is the title of the paper. So as I have told you, this basic paper deals with the how to spend the test time compute. When I say test time compute, it basically the time that it uses during the reasoning for a given task. So that is called the test time compute. So there are two ways to spend that compute. One is the parallel slicing, and another is the sequential scaling. So basically, in parallel slicing, you take most frequent answer, which are the small answers we take, and then you do the majority weight on the top of that, and then you take the best one out of that. So that is called the parallel scaling. So as far as then the sequential scaling is basically you build a chain of thought. So when I say chain of thought, that means thinking step by step. You build a chain of for every the input token that you have got, you keep on adding a new token, building a long chain out of it. So that is called the long chain of it. That basically induces long reasoning traces. So the goal of this basically paper is to quantify and explain the trade-off between sequential and the parallel scaling or test time compute, which is also the inference time compute for LLM reasoning task. So this is the basic idea behind the paper. So let's move to the next slide. So this is the introduction of the paper. So moving on to the next slide. So this is the basic graph that you can see for. So if I can show you to the, if I can enlarge my screen, I can show that these are the two experiments and the plots are provided for parallel and sequential scaling of transformer model, which is on a graph reasoning task, and the deep seek R1 distinct coin model on the same task, which is so when we apply the task using the sequential scaling, we can see that clearly even a slight. So when we see that even small reduction is chain of thought length requires a large increase in sample. So the sample, so so basically, for a very small change in the sequential scale, we can see there is a quite a huge jump in the best of an accuracy metric here. And while for the same accuracy to hold on, you have to take a lot of scaling to be done to achieve the same. So it clearly indicates that the so with the primary sequential scale, the accuracy is improving dramatically. So once the depth is, so basically this is the idea which is, portrayed here in the graph. So moving on to the next slide. So this is the main idea for, and this graph is basically built on the reasoning task. Okay, so moving on to the next task. Now, this paper is basically a very we need to establish this whatever we see in the graph. We need to establish this over the mathematical background and then doing the experiment. So basically, this paper explores both the ideas. First, it builds and proves the idea of having longer chain of thoughts over the parallel scaling. It first built a mathematical foundation on the top of it. Then it performs the empirical experiments to prove that intuition. So moving to the dismount. So what we will do is first of all on slide number 3 we will basically build. So we will basically build a graph reasoning task, and then we will perform this graph reasoning task using the sequential as well as parallel scaling, and then we will compare the result what happens with what. So we are setting up the test bed. So setting up the test bed requires connect. We are creating a multi-step chain of thought reasoning, and which stresses more on the depth of the transformer. So basically, this is the connectivity problem that we are, trying to build, and then we will task both sequential and parallel scaling to, get on this to compare or to perform this task and then compare the results. So given a graph, we have got three vertices S T1, T2, and then it is promised that the S connected exactly. So S is basically connected to T1, but not both. So basically, the job is to identify what is the connection between S, what is the connection the S is having, whether it is connected to T1 or T2. So this is called symmetric problem, symmetric connectivity problem. So, so the data set that we are constructing here is two identical disconnected component. One contains T1, T2, and other contains remaining large data set. And this is the input parameter basically, which will give the undirected edges plus IDs of ST1, T2. So this is the part of the paper which is providing, which is coming from this definition one. It basically defines. So if we go to the paper here, we can easily see this is the task. So this is the graph reasoning task that we are building to test both the intuition parallel, the parallel scaling and the sequential scaling. So by this definition, we are establishing ST1, T2. We could have established ST2, ST example also, connectivity problem also, but the reason is that ST is not, very symmetric problem. In this case, either S will be connected to 2 or not. But here in this case, S is must to have a connection. Either it can have a T1 or T2. So this is creating a symmetric problem, while this will have only a asymmetricity in the problem. So this definition 2 is more suited for our problem statement. So going back to the slide, so this is the task that we have set to test both the tasks. Now let's build some mathematical intuition that why the depth is more than the breadth and why the depth scores more. When I say depth, that means the sequential, building a sequential chain of thought. And when I say breadth, that is the parallel small number of tasks and then selecting out of it during the doing the voting. Okay, so this is the layman in the theorem. This is the layman way of explaining a theorem, which basically says for a bounded depth, limited precision transform on ST1, T2 connectivity task. So basically, the transformer is known as bounded and depth. Why the transformer is known as bounded and depth? Because transformer model is having a fixed number of layers which cannot be expanded, whose weights and active and the weights and active the activation function uses the very low precision floating point numbers. So the precision is also low. So when I say bounded depth, that means the it has got the fixed number of layers. So when you have got the large input layer, you need to build a large, large sequence, large, chain of thoughts, which is not possible because the layers are not going to expand, right? So these are the two intuition. So this is basically, the parallel scaling fails and polynomial constant length in a chain of thought with majority best of n achieves. This is the mathematical detail of the problem. Now here you can see one more thing which is called a TC naught. Now TC naught is a it's a kind of shallow circuit model that can mix multiple inputs which multiple it's basically it's a digital circuit that consists of multiple simple and majority gates, and then it put some operation on the top of them and then perform some sequential task. So in a way, this TC naught, which is a kind of shallow circuit model, some way mimics this bounded depth finite precision transformer. So in a way, TC naught is nothing, but it is some kind of we are trying to replace the transformer with some kind of TC naught and then prove it that TC naught, which is performing the parallel scaling, it will fail, right? So this is the mathematical intuition. So the way there is a proof for that. There are four types of lemma that is given, and then using the lemma for connectivity, it is proved that the LC T naught with the with the on the similar problem, it fails, right? So it is not able to go beyond a certain number. So that's why the parallel scaling is also, this is the mathematical foundation which clearly indicates the depth is better than the breadth. Now it's coming to the second thought of this number. So there are, so what we have achieved in theorem one, basically the theorem one in principle clearly states that By depth first, allocate compute to longer chain of thought before adding samples. And then you cannot trade breadth for depth. So that means so increase in the number of breadth can never compete in the depth for reasoning kind of task. So if you always need to take the more and the more depth kind of you need to increase the depth of the model. You need to increase the chain of thought to excel at the reasoning activity. Okay, so holds for bounded depth transformer under the standard assumption TC naught, which is again the shallow, the digital circuit, which basically mimics our transformer, which is bounded depth. So this is the achievement of the theorem one, which clearly indicates that the depth cannot the increase in number of breadth, any increase in number of breadth cannot compensate for the depth. When I say depth, it means the increased long chain of thought. Moving to the next part of the paper. Now, when we go to the paper, that basically introduces two more things. One is that it gives rise to, let's say, I have already given theorem one here, which was based on some definition. So this was for the problem. So now, other thing that paper introduces us is to the two more definitions, which is definition three, and then we have got theorem two, definition four, and theorem three, which basically is a part of this whole intuition, proving this whole intuition. So let's move to the two-path family and theorem 2. So basically, when I say two-path family, that two-path family problem is coming from the what you call it as the definition 3. Now, when we go to definition 3 here, the definition 3, if we go here, so definition 3 is nothing but it introduces the idea of vertex query model. So when I say the vertex query model, when I say the vertex, so the definition wise, it is stating that. So the definition wise, it is stating that connectivity is implementable in a vertex query model VQM if it takes input as and can only access graph G through neighborhood queries. So what does it indicates that? So it clearly indicates that at every graph or every node of the graph, so what does this indicate? This basically introduces the idea of vertex query model. Now the vertex query model, when I say that model, what it says is you don't see the whole graph. So it only asks the neighborhood queries. So this model basically do the each query. So this model, it basically does the local exploration in the nearby areas. It basically asks the address or the chain of thought which are attached to a particular node. So it goes to a particular node and then it asks for what are the nodes which are connected to it, and hence this way it gives rise to chain of thought. So on the top of that, it also defines another stricter version of this, which is called vertex query model, where algorithm can only initially query S and subsequently can only query vertices in the set. So this is putting another constraint on the top of the VQM model that we already had, that basically only can acquire about the in a graph it can only acquire the neighborhood queries, not beyond that. So in this way, it is not having the clear picture of the whole graph, and that is so basically the number of queries here can be substituted as sequential budget. So this basically analyzes the sequential budget, and then that sequential budget in a way indicates what is the length of the chain of thought. So this is what this whole definition put this basically this whole definition puts the idea of VQM model, how it works and what it indicates. So if we go into the detail of that, For the first depth transformer have limited multi-hop reasoning in the graph in chain of thought. So if you make the reading from here to here, it basically introduces the key takeaway here is that the sequential compute must scale with the path length. Without that depth, no aggregation trick bias the accuracy. So basically, you need to have the increase in the depth. Without that depth, the accuracy cannot increase. That is the basic idea behind uh, this VQM model. So this is what it is showing. So this is the graph that you have already built. So 1 to 4, 3 to 12. So this is the prompt basically that we have given 1, 4, 3, 12, 3, 12, 11, 5. So this is the scattered version of the edges that we are providing to the prompt. Now the task is to 10 or 30, to 10 to 13 or 6. So basically you have to go 10 to 13 and then to 6, right? So again, if we compare with the task which is S1 to T1 or T2, we have to go one by one. So we are not increasing the depth. So we will go every vertex. And if our chain of thought is not long enough to the number of vertices that it does have, it will drastically fail. So it will not be able to reach to T1 or T2. So that is the main idea. So to put that these things, this is the theorem 2 which is built on the intuition of this intuition, which basically tell which which basically tell uh, so minimum number of equivalent needed for the graph, considering the graph G for the disjoint path L greater than 3, and then we suppose. So basically it gives the two things. One is the order of L queries are sufficient. For the VQM to work accurately, if you want to reach from here to here, you need to generate a query which is of the order of length L. That is the first thing that it establishes. Second thing is that omega L queries are needed. So when I say omega L, now this has got its proof in its appendix, which basically computes the number of queries should be less than or equal to L minus 2 by 2 queries. So the probability of correctness of the S1 connectivity is exactly half, right? So in a way, it is putting a limit that the probability of finding its the connection is cannot exceed beyond half. So this is the limitation that this theorem is putting on the definition, or basically on the VQM model. So in a way, theorem 2 is basically putting some limitation on VQM model. Now to overcome that, there is a concept. There is a another concept that is called that is introduced, which is called a bridge graph. So bridge graph is an undirected graph parameterized by non-negative integers, where at every node we indicate four parameter: depth, short, long, and dead end. It is constructed as follows. So you can see the idea. So at every path between two vertices or the two nodes, one length we call it short. So to connect from vi to vi plus 1, there are two lengths. One is short, one is long, and there is another one path and a path from vi of the dead end, which is basically this. There is a three length. One is short, one is long, and one is dead end. So which basically indicates that it will not reach anywhere. So these are the three paths that we have indicated. Now, so now we can theorem 3 basically puts a restriction on VQM. There is a still gap between sequential and parallel scale, even in regime. So basically, theorem 3. So the definition for basically this construction is very much intuited, or this idea of bridge graph is introduced. This is because at every branch uh, you need to take three decisions. Either you will take short, long, or dead end. So with limited look ahead, wrong choices compound across depth, and it stresses test for multi-step reasoning. So this is basically this definition is giving to the bridge graph concept, and our models which we are putting for the so this can be this is basically we are building a multi-step reasoning, stress test for the multi-step reasoning, that one by one it builds the chain of thought on the top of it. So how accurate it is, right? So now there is theorem 3 built on the definition 4, which basically consider an algorithm in restricted VQM model solving ST1T2 connectivity union between two bridged DL2L0 graph, where S is the starting node on one end graph and T1 to 2 correspond to the copies of the two node. So basically at every node, so these are the two uh, so if you carefully analyze this graph here, it is building, this graph is built on the basic idea of this graph. This is the kind of bridge graph. Now, so basically it puts on a restricted VQM model. You can only start querying it at and then expand to neighbors you have already discovered. So query budget in a way is a sequential chain of thought length. So that is the idea. Now, here we can clearly see the sequential scaling succeed. If you spend roughly the shortest path length worth of queries, right, you can reliably disambiguate each intersection and follow the short branch and reach the correct target with very high probability. So what I meant to say is, at you can spend roughly the shortest part. So whenever you query at each end, it basically there are three things. One is the short, one is the long, and another is of course the dead end, which is of course you will know. So to query those three things, you are very much guaranteed to reach at your target, right, with a very high probability. Now here the parallel scaling fails because if your query budget is only constant factor above the shortest path, that means you are not querying in the order of your length, then you will never be able to reach to your target, right? Then at each intersection is essentially a guess with a constant success probability. Over intersection, the chance of tracing the right route decays. To recover accuracy by majority, you would need independent short runs, right? So key takeaways here is, so this theorem tree clearly put a stress test where, so this is the way we are putting some kind of stress test to check the multi-hop reasoning test for both the models. So when we do the sequential scaling, we can see we have succeeded, while with the parallel scaling we have failed, right? So the key takeaway is, on a bridge graph, depth is necessary, that is the longer chain of time is necessary, and breadth is exponentially insufficient. So that is the main idea. So let's move to the slides now. To so this with the graph I have shown to now the empirical evidences for sequential versus parallel scaling using theorem 3 that we have just studied. So this is the model setup. We have taken an open source model, small Mistral LM, with 4 layers, 4 heads, feed forward network with the 128, and context with the 400. So pre-training is already there with the 200 epoch, and these are the pre-training parameters, which consists of epochs, batch, and learning rate. So the prompt that we have given, shuffled edges plus thinking step by step. And the metrics that we define is decision accuracy and the evidence accuracy. So when we do this experiment, what we indicate is, what the bar charts clearly indicate. If you go to the bar chart here, we have clearly seen that the path, the DFS has got, so if you see here, so with the increase in depth, DFS training yields very high evidence accuracy, almost close to 1. Can you see? This is the DFS. It is achieving almost accuracy close to 1, while the walk 40, walk 30, walk 25, which is nothing but the walk L strategies, as L increases, evidence and decision both is declining, right? So and of course the shortest path method is somehow able to achieve a better accuracy than walk L strategies. So this is so here also it proves the intuition that the depth beats breadth, which means pushing longer COTs improves performance more than adding parallel sample consistent with theorem 3 message. So this is what theorem 3 explained to us. This is the mathematical detail which has come from the appendix of the same paper, which has proved this. This what is the success rate. So success is always greater than 1 minus exponential 1 to the d to the power delta square. D is nothing but number of layers, and delta is nothing but. So delta is nothing but the number of dead ends basically. So when you do this experiment, it is one with the lower this number is, higher the number of d layers, higher the number of greater the number of greater the value of d, the greater is the lower the value of exponential and higher the value of success. So in a way, it is very much close to one. But here, if you see in the theorem three parallel phase, what happens is success is less than half exponential omega, which is nothing but the order of the omega is the order of basically the queries basically. So here it is d delta square. So the more you have got the d, the lower the value of d, it increases f. Despite all that, the lower the maximum value the exponential can get is the more you increase the half the lower the value is, and more it becomes close to half. So in a way, in some way, it is putting restriction around half. So this is the experiment, empirical evidence for the. So the another experiment that we have done is basically using the bridged graph that we have done, and based on the bridged graph reasoning task, we have created. We have done the graph family with the short equal to 3, long equal to 5, and dead end equal to 3. That is the parameter of the bridge graph that we have provided. Data set consists of two randomized copy, right? So the goal is decide whether connects to A, this is the same connectivity task that we are judging our model on. So the goal is decide whether connects to A or B, which means connecting to T1, or decide whether it is, so this is the spelling error. So basically it to decide whether it is connecting to T1 or T2. So this is the evidence accuracy. We can clearly see the depth of bridge, the depth of bridge graph and the sequence scale. So once it passes some threshold value, the sequential scale has got a huge jump, right? And once we have got the depth of the bridge graph increase, the value is in a way is dipping to some value. But after threshold, we can clearly see that DFS is jumping like anything, right? So the evidence accuracy score is pretty high. So this is what the experiment consists of, and with this experiment, we have we in a way we have established that the deeper or the longer the chain of thoughts are, better it is able to utilize the test compute, and it will be very good at reasoning power. So this is the basic idea behind this paper. So thank you.